Hello guys, this is Mehdi. So today we want to start our video lectures for transform calculus and the partial differential equation ENGR 311. So I try to give you some short lectures on all the topics that we're going to cover in this course. For the first lecture, so we're going to start with chapter 4 of your textbook. We want to talk about the definition of Laplace transform. Then we talk about some basic definitions that we need for defining Laplace transform. And at the end, we're going to solve two simple examples. The first is finding Laplace transform of a constant function like ft equal to 1. And then we find the Laplace transform of an exponential function, ft equal to e to the power of 8. So for definition of Laplace transform, at first we have to know what transform is. So transform is an operation which transfers a function into another function. So in the past you saw some transforms. For example, integral is a transform. So then, for example, you have a function like t squared. Let's say we have a function like t squared, and you apply one transform like integral, so I call it integral. So you can see that when you apply integral to your function, you will end up with 1/3 t cubed. In fact, you have a transform that transfers t squared, one function, to 1/3 t cubed, which is another function, and you can write the integral of t squared dt is equal to 1/3 t to the power of 3. Another transform that you had in the past is derivative. For example, if you apply derivative to the same function t squared, so the transform that we have is d over dt, so you will end up with another function which is 2t. So in fact, d over dt of t squared is equal to 2t. So you can see again, you have one transform, which is derivative. It transfers one function, which is t squared, to another function, which is 2t. For Laplace, we have a transform as well, and it transfers one function to another one. For example, for the same function, when we have t squared, and if I apply Laplace transform, so I can show Laplace transform like this, so it's called Laplace. So it transfers this function to this function, 2 over s cubed. So t is one variable, s is another variable. So for finding Laplace transform, so I'm going to explain it in detail in this lecture and other lectures. So this transform is Laplace transform, and I show it like that. So Laplace transform of t squared is equal to 2 over s cubed. So it's for definition of transform. Now we want to see what Laplace transform is. In order to define Laplace transform, we have to know some basic definitions. The first definition that we need is improper integral. So as you can see here, improper integral is defined as a definite integral that has either or both limits infinite or an integrand that approach infinity at one or more points in the range of integration. So in fact, it has two definitions. So for the first definition, the first part of definition that says a definite integral that has either or both limits infinite. So let's see how it is. Let's say we have a function like we have integral like the integral from, let's say, 0 to infinity k, which is a function. It's a function of two variables, s and t, and the times, for example, ft dt. This integral is improper integral. Why? Because here we have one limit which is infinite. So I can write this integral like this. So it's equal to limit of integral from 0 to b when b approach infinity, k, s and t, ft dt. So here you can see that the integral that we have is improper integral. For the second part of definition, which said one integral, that integrand is the part, this function that we are integrating from. The integrand approach infinity at one or more points in the range of integration. So here we have the range of integration from 0 to infinity. If at one point this function approaches infinity, so again this function is this integral is improper integral. But for defining Laplace transform, we just focus on the first part of definition, a definite integral that has either or both limits infinite. Now for this integral, we can define two other parameters. This integral can be convergent or divergent. How it's divergent, how it's convergent? If this limit exists, I mean it ends up with a number, so we call this integral as a convergent integral. If this limit does not exist, so it means that it approaches to infinity. In this case, we call this integral divergent integral. So I write definition. If for the limit that we have, if limit of integral exists, so the integral is convergent. If limit of integral does not exist, so the integral is divergent. Sorry if my handwriting is not very good, but I try to do my best. Okay, so for defining one Laplace transform or Laplace transform of a function, we need one improper integral which is convergent. So now we can see how we can define a Laplace transform using these two definitions. So for Laplace transform of a function, if you want to define Laplace transform of a function, so here I can say Laplace transform. Laplace transform, so it says let f be a function defined for t greater than or equal to 0, then the integral is the integral of e to the power of minus st times ft dt from 0 to infinity is said to be Laplace transform of ft, provided the integral is convergent. As a result, here you can see that we have one improper integral, and the integral should be convergent if you want to have Laplace transform. So if I want to write Laplace transform of a function, first of all, as I already said, Laplace transform is shown by this symbol. So Laplace transform of a function like ft is the integral from 0 to infinity e to the power of minus st ft dt. And it's going to be a function of s, and we usually show Laplace transform with capital letter. So it's going to be a function like f capital S. So if you want to find Laplace transform of another function like g t, so we will end up with the function and we call it g capital S. So we always use capital letters to define Laplace transform. So now we can use this definition for different functions to find the Laplace transform. We start with very simple function, a constant function, and we find Laplace transform of ft equal to 1. So as an example, you want to find Laplace transform of ft equal to 1. So in order to find Laplace transform of this function, what we have to do, we have to use definition of Laplace transform. So we have Laplace transform of 1 is equal to the integral from 0 to infinity e to the power of minus st ft dt. So in this case, ft is equal to 1. I just plug 1 here. So as a result, we will end up with the integral from 0 to infinity e to the power of minus st dt. So you know how to find this integral. It's very simple. So it's minus 1 over s e to the power of minus st. And then we have to apply the upper limit and lower limit to find Laplace transform from 0 to infinity. So what happens if I apply the upper limit? So I just factor out minus 1 over s. So here we have e to the power of minus s times infinity. And then I apply a lower limit. So we have e to the power of 0. It's equals. So now we have to find e to the power of minus s times infinity. We have to consider two different cases. Imagine s is positive. If s is positive, minus s is negative, minus s times infinity is going to be negative. So we have e to the power of minus infinity. So it ends up with 0. For the second case, imagine s is negative. So if s is negative, we have a negative here. Negative times negative is positive. So we have e to the power of infinity. E to the power of infinity is infinity. As a result, this integral is convergent only if s is greater than 0. So we assume that s is greater than 0 and this part is going to be equal to 0. So it's if s is greater than 0. So now we have e to the power of 0. E to the power of 0 is 1. So we have minus here, minus here. Minus times minus is plus. As a result, we have 1 over s. So we can say that the Laplace transform of function 1 is equal to 1 over s, but it's just for s greater than 0. For less than 0, we don't have any Laplace transform. So it was a very simple example on how we apply definition of Laplace transform to find Laplace of a constant function. Now we solve another example. In this example, we want to find Laplace transform of one exponential function. So e to the power of at. So in this case, a is a constant. So it can be 1, 2, minus 3, anything. So a is a constant. In order to find Laplace transform, so what we have to do, we have to just apply the definition. So we have Laplace transform of e to the power of at is equal to the integral from 0 to infinity e to the power of minus st ft dt. So ft is e to the power of 80. As a result, I just plug it in the integral. We have the integral from 0 to infinity e to the power of minus st e to the power of 80 dt, and it's equal to the integral from 0 to infinity e to the power of minus, I just factor out minus here, so we have s minus a times t dt. So you know how to find the integral of this function, e to the power of minus s minus a times t, so it's equal to minus 1 divided by s minus a times e to the power of s minus a minus s minus a t, and now we have to apply the upper limit and lower limit. So here we have 0, here we have infinity. Again, I just factor out minus 1 over s minus a. So here we have e to the power of minus s minus a times infinity minus, and if I plug 0 here, so we have e to the power of 0. So if for this part again we have the same condition. If s is greater than a, so this part is positive, we have negative here, negative times infinity, so it's minus infinity, so e to the power of minus infinity is equal to 0. And if s is less than a, so this term is negative, negative times negative is positive, so we have e to the power of infinity, so it's going to be divergent. As a result, in order to end up with one convergent integral, s should be greater than a, and this part is going to be equal to 0. It's for s greater than a. And here we have e to the power of 0 is 1, minus times minus is plus, so it's 1 divided by s minus a. As a result, we can say that Laplace transform of e to the power of at is equal to 1 divided by s minus a for s greater than a. For s less than a, we don't have Laplace transform. So as an example, what's Laplace transform of, let's say, e to the power of 3t? So it's equal to, instead of a we have 3, so it's 1 divided by s minus 3. Or what's Laplace transform of, for example, e to the power of minus 5t? So it's equal to 1 s minus a is minus 5, so minus times minus is plus, so it's s plus 5. So we could find a Laplace transform of this function as well. So here we finish the first lecture. In the second lecture, we're going to talk about Laplace transform of more complex functions.